Hello, everyone, and welcome to the first episode of Mechanical Engineering's four-part series of conversations where we look into how digital engineering tools are molding the next phase of design and manufacturing. My name is John Kozowatz, Senior Editor of Mechanical Engineering Magazine and ASME.org. Today's conversation is focusing on, is digital design and simulation the future of product development? Joining me today are two guests who will discuss the greater importance of CAD and its future, how augmented and virtual reality are advancing design, how designers may leverage the power of cloud computing, and how a digitally connected network fosters online collaboration. Our first guest is John Wade. He is a professor of practice at University of California, San Diego's Jacobs School of Engineering. He's the director of Convergent Systems Engineering, designing transdisciplinary education and research programs. Among others, his research includes the use of technology in systems engineering and STEM education. Our second guest is Christopher Ritter, the director of the Digital Innovation Center of Excellence at the U.S. Department of Energy's Idaho National Laboratory. His expertise is in software engineering and development, systems engineering, software integration, and database management. So welcome everyone to our digital engineering conversation. Before we begin, I'd like to thank all of our sponsors. Please make sure to check out the resource section on your console to get more information. So let's begin, and let's start with Chris, whose work in the digital development of the versatile test reactor at INL was described recently in the pages of Mechanical Engineering. Your research into the idea itself showed a lot of examples from various industries. What impressed you about the possibilities, and what other options really are there? And maybe even before we get into that, maybe you should just describe what the versatile test reactor is.
Sure. Thanks, John, for the introduction. The versatile test reactor is a 300 megawatt nominal thermal reactor that is under design at INL for the establishment of a new sodium-cooled fast reactor test reactor capability. So in building a new plant like that, and it's a first of a kind, right? And it's really a one-of-a-kind facility, there's a lot of challenges, right? As we don't have to point to data points to show that really any project over $1 billion, right, has a 65% chance of failure, where failure is defined by 25% of projects being over, 25% over budget or 25% behind schedule. And so if you look at projects like this, right, from the get-go, right, they're very challenging to construct. So the project manager of VTR at the time, John Bumgarner, looked for ideas for what could de-risk us in building something like this. And he came to digital engineering and virtual design and construction as one of the key ways that we were going to reduce our risk in construction of the VTR. And so in building the VTR, we have a relatively complex digital engineering ecosystem that we've developed and that is continually being developed as we build the plant to enable a digital engineering system for design of the plant and then a digital twin once the plant operates. Since at least in my opinion, a digital twin is defined as your designs, your full physics models, right, and CAD models connected to a physical plant that exists. And so I think what excites me, to answer that question about what we see today, I think if you look at the Department of Defense, you really have to give them credit for starting this renaissance that we're in right now. They developed the digital engineering strategy a couple of years back, and that strategy has actually been kind of our playbook for how we're implementing digital engineering at INL. And so DoD has heavily emphasized 5 key areas. Maybe that's all I'll kind of talk about what I see as kind of exciting right now. So the first is the use of model-based tools. So that can mean different things to different people, but it depends on what part of the life cycle you're in. So model-based system engineering, to me, is where your upfront design, right? So from your original stakeholder requirement or your ConOps through your detailed system-level diagrams, right? So we're talking about like block definition diagrams, activity models, things like that, right? Model-based system engineering really is the forefront of how to evolve system engineering forward. DoD has been doing this for actually a number of years now, and we're seeing it more and more in the energy space. The National Reactor Innovation Center has taken a full dive into MBSE. And in In aerospace, Boeing is using MBSE concepts too. Product lifecycle management, so if you're building a solid model in CAD space, that's really popular. And there are a lot of really great tools out there that already do a great job of connecting the CAD ecosystem together. The negative is a lot of them are vertically integrated within a typical vendor stack, but it is exciting to see that at least in that stack, they're integrated together. Building information management. So that actually was one of the original innovations that kind of inspired the digital engineering strategy from DoD. And so that really did change kind of what they were thinking and what was possible. And so BIM, there's a number of tools out there that do BIM really well these days too. Once again, very commonly integrated with one company stack, but at least you're able to integrate within the CAD sphere pretty well these days. So the second tenet is an authoritative source of truth. So not a single source, right? It's not one database for everything, but it's an authoritative source. Many companies are in the process of implementing various aspects of a authoritative source of truth, because an authoritative source, right, is supposed to connect all the way, right, from design through operations. So I don't think we could point to a single example of someone who's done everything perfectly, but I think we're getting examples, right, in the industry where we're like the Boeing, not Boeing, the GE engine programs, right, where we're seeing some pretty good evolutions in the space. They're claiming like about $1 billion in savings in using digital twinning, for example. So at INL, our approach has been taking an open approach. So we use COTS tools, but we have an open source data warehouse to do the authoritative source of truth that we call deep links. And we put it on GitHub so everybody can use it. And the third tenet is innovation. So we see some really great research happening at universities and laboratories and federal research centers that really make this possible. So obviously at INL, we have a lot of multi-physics work, research, and we have a lot of research in artificial intelligence applications of this. And then we have university partners that are learning how to apply AI to this as well and how to do some automatic meshing to make this possible. The fourth tenet is environment. I think in industry is really leading the pack here. So cloud, I think cloud computing right now is really the big enabler to make these possible in geographically dispersed areas. And most projects are multiply dispersed across the United States or internationally. So cloud computing really makes that possible. And then the fifth tenet is transformation of culture. And that's where you really look for people like John and the university sphere to kind of transform that culture before they even graduate school, right? They come to us pre-trained. That's the dream, right? So hopefully that helps to answer that question. Okay.
And it is complex. There's really, there's not one-stop shopping for such a complex project like this. So talk a little bit about the challenges or the difficulties in standing up the system.
Yeah, so it starts with tool evaluation, right? So you have to pick your tools. Commonly, it could take some companies a year or more to pick tools. We didn't have that kind of time. So we pretty quickly got industry experts together, and some tool selections were made in a couple weeks based on data that we had from industry. So if you could accelerate that process, that helps. The other thing is standing up the tool. So most people think I bought the tool, I'm good to go. No, right? You have to set up the tool to work for your project, and that's really complex. So we have experts on my team, but we also rely on the vendors typically. We right away wrote contracts for each vendor, right, to make sure that we got their experts involved in the architecture development. And then the other kind of issues are, how do you stand it up? Where do you put the software? We originally put it on our internal network, but honestly, that latency was way too high. Our latency peak values went down by 1,000x when we moved to the cloud, for example. And so we got a huge advantage by moving, but these are hard things. You don't have them already, right? You got to get that infrastructure in place, like cloud computing or HPC. You've got to get those tools acquired, trained up on your folks, and then you have to start integrating them together. Some tools have integrations built in, at least within their own ecosystem, but typically they don't have integrations across the silos. And so more tools, like some of the stuff we're building, is being open sourced and being made available, but it's definitely an evolving science. And then the hardest thing, of course, is the training of people and getting everyone to really buy in and use the system, right? Give up those Word documents and move to this new world.
And that's a pretty good segue for you, John. So give us some examples of the complexities that engineers have to deal with now and how these digital engineering design tools help meet the challenges.
Sure. Thanks, John, again, for the fine introduction and inviting me to be here. We live in an engineered world, and I think sometimes we forget about it because it's changed so very, very rapidly. You have to remember that the internet really came into being for the general population around 1995 with the release of the Netscape browser. So that's 25 years ago. So really, before that, the internet was a curiosity used by research labs and that sort of things. Now the world's totally dependent on the internet for just about everything that we do. Everything in commerce, business, engineering, entertainment, and just about everything else. And we've certainly seen that with the COVID situation of just how important it is to us. We're entering the fourth industrial age. The first industrial age was, mid 1700s, 1800s. Hand production moved to machine production. The second one was getting electricity, telegraph, and railroad, being able to move things around. The third was really the digital revolution, where we got computers and communication technologies and those sorts of things. And around 2011, the term fourth industry revolution was coined. And it's really about data exchange, cyber physical systems, networks of things, cloud computing, cognitive computing, artificial intelligence, and the rest. Many of things that Chris just spoke of. But it really changes the way that we work. It changes the way that our lives work. It's rather than being directed, it's much more collaborative. And so if you look at the industry, if you look at the factory of the future, it's really a place where there's cooperation between machines and humans, sort of moving in time, understanding what's happening on the floor, using that data to make decisions, and so on and so forth. And there's a number of companies that have mastered these technologies, or at least are leading the way. And they're the companies that have the highest market cap, in the world. So the Googles, the Amazons, the Facebooks, the Microsofts, the highest valued computer firm or automotive firm, Tesla and such. They understand that the data and understanding data and using data and these technologies to make decisions more rapidly is really the competitive advantage that one has moving forward. And so it's really driving, everything that we're doing. And so when you look at these capabilities, engineering has to use those same sort of technologies in order to keep up. And so the question is, how are we using data to do our engineering? Do we know, for example, what's happening on the installed base of our particular products to know how to engineer and design it better? Do we know what the rest of the engineering team is doing so that we can collaborate more effectively? Are we using AI and machine learning to extend our capabilities? Garry Kasparov, the world's greatest chess champion, was beaten by Deep Blue, a machine, a number of years ago. But he said, a machine can beat a human, but a fairly average chess player with a fairly average chess playing program on a laptop can beat both of us. And I think until we get to the place where we are able to be better than any humans and also better than any machines, we're really not using the technology to its full benefit. I'm from the electronics industry, computer industry, and spent a fair amount of time there. And for the last 30 or 40 years, we've really been leveraging tools, CAD, simulations, and all the rest in order to keep Moore's law going, where we're sort of doubling, every couple of years in terms of transistor count and complexity. And so the question that we would have at the beginning of every project is, how much money do we want to spend on humans? How much money do we want to spend on computing? And how much money do we want to spend on software CAD tools? And it was substantial, the amount of money that was spent on the computing side and the CAD tool side. And I think we have to get to that place, with general engineering, so that we really understand that there's great value in being able to collaborate, with CAD and such. And I think we have a long ways to go, in that space. And we're only really sort of scratching the surface with respect to what can be done with data, machine learning, AI, working with humans in the engineering process.
So it's it's an almost brand new concept that engineers and others now have to deal with. The advancements are happening faster than someone can comprehend almost. Is that a true statement?
I think it's a true statement, but again, it is happening in a number of different places. So I mentioned a few of the companies that have really are out in front of this, and the challenge is that there aren't that many people who have been trained, in these skills that have the background. So if you think about classic engineering, we think of calculus, we think of Newtonian physics. That came about in the 1600s. And we think about thermodynamics, Maxwell's equations, those are 1800 technologies. Then you think about, the computer science side of things. So computer languages really came out sort of the mid, 1900s. And what's sort of surprising to me is there are a number of engineers that graduate and don't have a solid handle on programming. They're not capable programmers. And I think software is really the language of engineering. And so certainly every engineer that graduates needs to have a handle, and they need to be competent and proficient, in programming. Where we're really behind is in the area, I believe, of data science and in systems. Post-secondary schools, and actually K through 12, was really designed during the industrial age. And it looks like an industrial org chart where you've got mechanical engineering, electrical engineering, computer science, and so on and so forth in engineering disciplines. But it's really not possible to do anything unless you've combined all those things. And so, we're moving away from this sort of factory model of moving things through departments to the place where we're all collaborating and we're all working together. And so we need many more people who are sort of skilled and understand systems, who are transdisciplinary, who can work in all those different spaces. And I think that's the place where we need to make great breakthroughs in post-secondary education. And one of the things that we're attempting to do at UCSD and the development of our convergent systems engineering program.
Okay. So being quick and nimble, industry prides itself on being quick and nimble and putting a product together, designing a product. How quick and nimble are the engineering schools in meeting the demands of industry right now?
It's a very good question, and it really varies. I would say that some are not nimble at all, where you've got faculty who like teaching their current courses and they don't really want to change those courses. And then there are other institutions where things are actually moving, pretty quickly. And I think what's missing is some of the feedback loops in the system, which is ensuring to make sure that the students that are graduating are able, competent, and sort of tooled in order to be lifelong learners and also to be able to, competently do their engineering. And so what we need to do is really, I think, partner more closely with industry so that we can get better feedback to understand what are the latest changes, what are the latest challenges that you have, and make sure that our programs are delivering on those challenges. And industry is certainly willing to do that, and numerous educational institutions are willing to do this as well. And I think as we get into this century, there's going to be clear winners and losers in the game of education. Those that get it and move quickly, I think, are going to be seen as the preferred places for education. And they're going to need to do it in a way that's fairly financially prudent, because education just has to be more accessible to more people, and it has to be accessible over their entire lifetime. The fact that education debt in this country is greater than credit card debt is not something that's sustainable. So we really need to get to a sustainable education model, leveraging technologies and educating students so that they can contribute in this world that's changing so rapidly.
Okay. And Chris, you had mentioned earlier that in standing up your system at INL, one of the things that you mentioned training and you mentioned collaboration as being key to all of this. So how difficult was it to bring in a workforce that was familiar with all these tools and what it takes to put them together?
It was pretty difficult, I would say, out of the box. You don't have any one person who knows how to use every tool, and that's always going to be the case, right? And so what we do is we bring people together to know how to use certain types of tools, right? And we bring them to collaborate together to work on problems. So, for example, for VTR as a whole, we have mechanical, civil, electrical engineers. We have folks that are experts in computer science and system engineering as well, collaborating to make this possible. I think if you look at the education sector, what we're starting to see more happen at the universities is collaboration with engineers and computer scientists. And I think that is really great, because I think, as John alluded to, I think having data systems and data connections are really difficult, but computer scientists are really great at writing code and architecting how the code should look. But we really need to collaborate with those engineers, right, as to what these systems need to look like and how those data interfaces should be. So it is a collaborative effort that takes pretty much every domain that it takes to build an asset involved to make it possible right now.
Okay, well, let's drill down a little bit into that, into the role of the design engineer. How is it changing now? For instance, how involved should a design engineer be in dealing with simulation, for example? Do they just design it and hand it off to someone else? How much more is expected of a design engineer?
So, it's an interesting question because it's posed in sort of the way of, should everybody be a draftsman? Or should the design engineer sort of hand their design off to the draftsman and then let the draftsman sort of put it into the computer or so on and so forth? And I think you really have to be both. You have to be a part of the system. The notion of taking it and handing it off to someone, you're now starting to lose the excitement, and where a lot of the innovation happens is where you actually get the design and you start the iterative process. It's very iterative and organic, the way design is actually done. And so if you talk to a data scientist, they'll tell you that, it's easy up front to say, this is what I want to do, but it's not until you actually get into it and you start working the problem that you start learning and you start understanding. And so I think that what we need to create are sort of learning systems where we've got the OODA loop, the observe, the orient, decide, and the act, and we need to figure out ways in order to accelerate it. What's interesting to me, what I see with artificial intelligence and machine learning, it looks a lot to me like VLSI did in the late 70s and 80s, where there was this great technology, integrated circuits that was taking off Moore's law. It was doubling every year and a half or so, but there were only a handful of people in the world that could actually design it, because to design you had to be a semiconductor physicist, a material science, a circuit designer, and so on and so forth. And what's missing is those same sort of levels of abstraction, so that we can actually compose systems that are AI intensive systems without everybody being a data scientist and an AI expert. And so I think the big revolution that's going to happen for us is the ability to sort of create those abstraction layers so that there can be optimization and innovation at each of those different levels without everyone having to understand everything. And I think people are really challenged today because we don't have those. And so you pull a bunch of people together in a room and you say, let's try to do this thing. And people are just running off in different directions. It's difficult for people to talk to one another. It'd be interested to me, Chris, to sort of hear how it worked for you.
Yeah, so so we could talk about VTR and we'll talk about NRIC, two different projects. So the Versatile Test Reactor program, we've kind of put a mandate. It took a little while because everyone was honestly working in paper documents prior in industry in this world. And so we moved everyone to a requirements management database approach, right? Where we would no longer think about things in terms of documents and think about things in terms of how the data flows. And so we were successful in moving most of our engineering team over to what's called the IBM Jazz ecosystem for system engineering. I had a similar thought as to you as to where we would go with them, right? I thought we would have the drafters maybe work with the engineers, but the engineers would be the ones using those BIM tools. So I personally got the training in one of the tools that we were going to use so that I could, understand it and use it. And I will tell you, it's still a little bit too clunky to give it to every engineer. So there is still some evolution that has to happen in industry and some of the actual design tools, right, to have it so that the actual engineers can be the drafter, right? And the drafters can be there maybe to help them with the more complex problems. We're not quite there yet. But at NRIC, we've been using model-based system engineering, so kind of the next thing, right? So you have requirements databases, and then MBSE is kind of the next path. So we have been successful there on smaller micro-reactor programs of having people move to MBSE. And so the actual engineering teams use the tool directly to create their system-level diagrams, right? So these are block diagrams, activity diagrams. They're integrated with the simulation at that level. Still, the CAD drafting is happening with drafters, but that is something we want to move to. And we're talking about using artificial intelligence and machine learning concepts to generate some of those CAD models at the system level. So, you create a requirement, you put in your physics calcs, and then it could generate for you, right, some basic models, right, off the shelf. And so that's the kind of stuff we're looking at as far as cutting edge there, but definitely the usability needs to improve those tools before I think we'll get mass buy-in by every engineer to be using the system. And that's probably similar to what you're seeing, John, right, in education.
So, in a similar vein, you're talking about artificial intelligence and machine learning that are being built into the tools now. How does the design engineer adapt to those tools? And does the simulation necessarily produce the best possible design for a product, or the most practical design for a product? Because you still have to build it. You still have to stand it up, whatever it is.
So I guess I'll take the first person to that question. So if you look at how AI is being integrated, so let's take IBM Watson as a use case. So if you look at the system engineering side, there's an IBM Watson plugin now for IBM Jazz Doors, their requirements tool. And so it will basically help guide you with requirements authoring, right? What we see a lot of times on projects with hundreds of engineers is not everyone's a great requirements expert, right? Writing good requirements, right? But if you have a tool like Watson, right, to sit there, help you, guide you through the process, it's really there as almost kind of like an extra bird on your shoulder, right, to help you through the process. It's not, you can ignore it, but it's there as help. And that's what we're seeing there. On the simulation side, so what we're seeing right now, what the cutting edge is, you know, at INL, we have a very huge investment in multi-physics tools. And we're starting to put more investment into reduced order models, right? So we can run those models faster. You know, HPC simulations, right, take, you know, lots and lots of cores, right? I mean, a lot of our HPCs in the DOE space are massive, right? They dwarf what most industry partners have available, right? And so we're trying to figure out how can we do those into numerical or artificial intelligence models so we could get similar results that you could run on your laptop. Or a small server. And that's the kind of research that we're seeing really where AI is augmenting there the fastest in the design side. Now in operations, you're seeing AI being used for predictive maintenance activities. And there's been a lot of success, right, on predicting component failure early so you can replace the component before you actually have an outage. And so that's the kind of work where we're seeing AI really applied heavily and being very successful.
Okay.
You know, the question's been asked, you know, when is the computer going to replace the human? And my response to that is, when will the computer know the difference between the data it's being fed in the real world? And I think that's increasingly the challenge for the engineer, is the engineer needs to know the difference between the limitations of the data and the real world. If they don't know that, then we can get into a lot of trouble because they can believe what they see without understanding the limitations of what it is that they're actually doing. So the digital twin is not the real thing. It's a representation, and you need to know the limitations of that that design. And the thing is, you can't make anything perfect, and it takes infinite resources to make something perfect. And so you really need it to be just good enough. You know, all models are wrong and some are useful. Is you need to put in enough fidelity to make sure that it's actually useful. And so I think that's the challenge of the design engineers, to understand the limitations of the tools, of the models, and be able to sort of work within that space so they know that what they're doing is going to work as designed. That's the challenge. And the fact is that if engineers aren't keeping up at that rate, we could be in for a lot of trouble as we have more and more automation.
Okay.
Yeah, John, I couldn't agree more. Just to throw a little sidebar.
Sure.
So Google's AI, there's an article in 2017 about thinking a turtle was a gun, as an example of where we could go wrong, right? So neural networks are black boxes, right? And often there's no explainable AI as the newest world there, but right now, a lot of our neural nets aren't explainable. And so sometimes you can change a single pixel and it will think a picture of a turtle is a gun, for example. And that's something we should all worry about.
Indeed. And that brings us to the end of today's conversation. Thank you, gentlemen. Let me thank you again for participating. Our next conversation in this series is November 17th, and we'll focus on how digital engineering is transforming additive manufacturing. And again, I'd like to thank all of our sponsors. Please make sure to check out the resource section on your console to get more information about them. Thank you all for tuning in, and I hope that you will join us for our next conversation.